recording has started.
Sir,
Yeah.
so I also got the answer approximately 55%.
Okay. Um,
So,
Atharva, are you there?
so even I got
Yes, sir. I
55%.
got
So even I
54%.
got 55%. Sir.
Okay. Atharva, are you there? Would you like to tell us how you got 44%? I don't know whether 44 is right or 55 is right.
So I will check my calculations, sir.
No, no, you don't need to check. All I'm saying is, can you tell us how you got the solution? Would you like to volunteer and tell us how you got the solution?
Yes. I will try, sir. Means I will.
Yeah, tell me. So
So
Atharva is
we
going to
first,
tell us the solution. Yes, go ahead, Atharva.
first we want to do, sir, heat of in enthalpy of SO3 formation, sir.
Heat of? Heat of this
Enthalpy of
reaction.
yes, sir.
Okay. At what? 25 degrees centigrade
Yes, sir.
for the reaction. Okay. Now, go ahead, Atharva. I'm listening. We are all listening.
Some minus 395.18
So this is minus 395.18,
minus of minus.
296.90. So that's heat of formation of products.
Yes, sir.
Actually, delta H0 products, formation of products, minus delta H0 formation of reactants. Oxygen,
No, sir, it's in standard state, sir.
correct,
Zero.
standard state elements in their natural state, elements and gases. Right, so tell me value. Yes, Atharva, we are listening. You can keep your mic unmuted. Only two of us are talking.
Yes, it is minus 98 point.
Yeah, Atharva, we are losing your voice. 98 point what? Atharva, is there a problem in your network connection? Otherwise, we can ask somebody else to volunteer.
Wait a minute. It's 98 minus 98.28, sir.
28 units,
Kilojoule per mole, gram more.
kilojoule per gram mole. Per gram mole of what?
SO3.
SO3 or SO2, they are the same because every 1 gram mole of SO2 reacts, 1 gram mole of SO3 is generated. So it is per gram mole of SO2 that reacts minus 98.28. That means 98.28 kilojoules of enthalpy will be released. Okay, go ahead now.
Sir, let X be the moles reacted, sir.
Moles of SO2 reacted. Okay,
Yes,
then
sir.
we want to do the material balance here. So if we are saying that our basis, what is your basis?
X kilomoles, sir. X gram mole.
Basis is x gram moles or basis is your feed you are saying? This is given in terms of mole percent. What basis would you want to take for doing the
100
calculation?
100 gram moles, sir.
Right, 100 gram moles
Total.
of the feed gas. 100 gram moles of the feed gas. 1 second. We'll just call just like that. For no reason they call. Yeah, so good. Basis is 100 gram moles of the feed gas. Okay, so now in terms of gram moles, if we write, it will be 9, 9 and 82. And then if we write for the products in terms of gram moles, if x gram moles react, out of the 9 moles, we will be left with 9 minus x. SO3 formed will be x. Oxygen will be 9 minus 0.5 x. And nitrogen will be 82.
Yes, sir.
Yeah. Okay. So material balance we have completed. All right. Now go forward.
So you want to calculate the heat of by Kirchhoff-Rosse heat of enthalpy at 450, sir, of SO3.
Okay. How? What are you saying? Heat of reaction or enthalpy of SO3 at 450 degrees centigrade?
For reaction, sir, means we have at standard set 25 degrees Celsius. We want to
Okay.
calculate at 450.
So we want delta H for the reaction at 450 degrees centigrade. Why 450 degrees centigrade, Atharva?
So it is outlay means it is state function. We can calculate at any degrees temperature.
Okay, so if we calculate heat of reaction at 450 degrees centigrade, that will be the heat of reaction at 25 degrees centigrade. That is standard in under the standard state. So delta H0 for the reaction. This is at 25 degrees centigrade. Plus, you have to integrate Cp from 25 to 450 degrees centigrade. But because temperature is given in terms of Kelvin, we will have to convert this into Kelvin. So this integration, correct me if I'm wrong, Atharva, integration would be from 298.15 to 450 plus 273.15, which means it will be 450 plus 273. So this will be 723.15 Cp of all the products minus Cp of all the reactants into dt. Am I right, Atharva?
Yes, sir.
Okay, so this would be delta H0 for the reaction at 25 degrees centigrade. This value we already know. This value is minus 98.28 kilojoules per gram mole of SO2. Now this will be 298.15 to 723.15 Cp of product. Product is now our SO3. We are talking about this reaction. We are finding out heat of reaction. The reaction we have written like this. So this would be Cp of SO3 minus Cp of SO2 plus half of Cp of oxygen into dt. Am I right, Atharva?
Yes, sir.
Okay. Only thing, take care that this whole thing, the units of Cp are calories per gram mole Kelvin, right? So this whole red integral will have units of calories per gram mole, whereas this minus 98.28 is kilojoules per gram mole. So if you want to keep the same set of units, we can either convert this 98.28 into calories, or we can convert these calories into kilojoules. Which one do you want to do, Atharva?
Sir, the CP value is carried into kilojoules, sir.
So this, if we have to convert to kilojoules, this integral we will have to convert to kilojoules. So we will do that. How do you convert from kilojoules to how do you convert from calories to kilojoules?
Sir, multiply by 4.18
Correct.
calories.
Multiplied by 4.18, that will give us in joules. And
So it is Kelvin, sir. One only, sir. Difference. Centigrade and Kelvin.
no, this is calories per gram mole. If I multiply by 4.18, that is joules per calorie. So this will be in terms of joules per gram mole, not
Yes, sir.
kilojoules per gram mole. So what you will have
Uh,
to convert
mul-
kilojoules?
multiplied by 1000, sir.
Multiply by 1000 or divide by 1000?
Divide by 1000.
Atharva, be careful.
Yes,
So
sir.
divide by 1000. Now both the terms have the same units. This also will be in terms of kilojoules per gram mole. All right. So you want to tell us the actual value finally? Everybody, I hope, assuming that everyone can integrate for themselves. Okay. So you tell us directly the value delta H for the reaction at
Just a
400.
minute, sir. Here only I made a mistake.
Doesn't matter, Atharva. You can. It is okay to make a mistake. That is fine. I don't know whether you are right or other people are right. I have no idea. But good that you have found your mistake. So this we will get. Okay, fine. Now what do you want to do? You can
Sir,
correct it later and tell us. Now how do you go forward?
sir, we want to calculate individual remaining gases heat of entropy
You
from
speak
300 to
slowly
450.
and you speak slowly and you speak loudly.
We want to calculate, sir, enthalpy of N2, O2, and SO2.
Okay, so we want to calculate enthalpy of feed gas. You want to say that's what you want to say?
Yes, sir.
Feed gas at 200 degrees centigrade.
Sir, no. So we want to by 300 degrees Celsius
Sorry,
to.
not at 200. It is at 300. Okay, now.
So we assume it's at reference point, sir. So it will be 0 for all gases.
Okay, so here is a point that I would like to make, that whenever we are talking about enthalpies and whenever the reactions are occurring, these standard states we have assumed, automatically we have assumed that our reference is 25 degrees centigrade, 1 atmosphere pressure. When you have said standard, you have automatically assumed this value, that your reference is 25 degrees centigrade. So I cannot take, if I say reference is 300 degrees centigrade and enthalpy is 0 for that, this is incorrect because it is inconsistent with our, we have already used these standard enthalpies. Atharva, do you agree?
Yes, sir. So
These
we want to take
enthalpy
25,
values,
sir.
yeah, so these values we have already assumed, not assumed, these values we have already taken for our calculations. If we have already taken these values for our calculations, unknowingly we have already assumed that our reference is 25 degrees centigrade, 1 atmospheric pressure. So what you should say is, now let us calculate the enthalpy of the feed gas at 300 degrees centigrade with respect to reference, which is 25 degrees centigrade.
Sir, I just have a question here.
Yes, sure.
So basically, we said that we have already set a reference at 25 degrees centigrade. That's why we can't set a new reference of 300 here, right?
Right.
So basically, what I'm just trying to say is, in this part of the problem, only the one we are calculating right now, what we are going to do now is to find the difference in the enthalpy of the products and this product stream and the input stream from 300 to 450, right? So for us, the change will be important. So here in this, only in this part of the problem, we can say 300 is okay to keep as a reference, right?
No, because we are not finding the change, because the moles of SO2 have changed, the moles of SO3 have changed. SO3 moles have been generated. How they have been generated? Some of the SO2 and oxygen have reacted, isn't it? It would have been okay to do what you are saying. That's what we have been doing when we did enthalpy balances without reactions. You remember that? I mean, we did enthalpy balances without reactions. We could take
Yes,
all
sir.
kinds of reference states. So in the dryer problem, we took maybe maybe we took enthalpy of the first stream as 0, right? Or the
Yes, sir.
dryer problem. Let me show that dryer problem. Where the dryer problem. Anyway, okay, wherever that dryer problem is there, we could effectively take any reference condition, because there was no reaction happening. Nothing was getting converted. It was only changing from one stream to another stream. But now that reaction is happening, some of these molecules have disappeared. Do you understand the difference between enthalpy balances without reaction and with
Yes, sir.
reaction?
Yes, sir.
In
So
whenever
SO3 has been created and
let me complete. Whenever we are talking about reactions, some of the molecules are disappearing. New molecules are forming. Right? 9 minus X molecules of SO2 have disappeared. 0.5 X molecules of oxygen have disappeared. And in their place, X molecules of SO3 have appeared. And therefore, we need to find out the change in enthalpies for X of SO2, 0.5 X of oxygen disappearing, and X of SO3 appearing. That change is what is calculated here. That change is what is calculated here. So whenever molecules are disappearing, we need to account for this minus 98.28 kilojoules per gram mole of SO2 that disappears. And that change we have automatically taken into account, because we have used these minus 296 and minus 395.18 as our values in the reference state. And therefore, whether we have liked it or whether we have not liked it, we have automatically assumed, whether knowingly or unknowingly, we have assumed that our reference is 25 because we have used these values. Otherwise, I would have to give you delta H0 of formation. I would have to give you delta H of formation of SO2 at 300 degrees centigrade. Right? So I would have to give you sulfur in the solid state plus oxygen in the gas state, giving you SO2 in the gas state. I would have to give you the CP value for sulfur as well. Do you agree with that, Shaurya Raj?
yes, sir. Yes, sir.
Whereas when we did enthalpy balances without reactions, whether it was a dryer problem, whether it was a cooling tower problem, whatever problem was there, when no reaction was happening, molecules were not disappearing. Whatever water was there, either it was in the liquid form or it was in the vapor form, liquid was changing to vapor without changing its form, without changing its chemical composition, right? No molecule was getting lost, no molecule was suddenly appearing. Unlike our reactions where 9x moles of SO2 and 0.5 moles of oxygen are disappearing, and X moles of SO3 are appearing. Okay, because we have used the standard enthalpies of formation. Otherwise, you would have had to calculate what is the enthalpy of formation of SO2 at 300 degrees centigrade, and for that you should have asked me what is the CP value for CP value for sulfur in the solid state. Am I clear, Shaurya Raj?
Yes, sir. Yes, sir.
So I gave a little long answer because many of you would have this doubt. Why do we treat reference differently for without reactions and with reactions? All right, Atharva, can we go back to you?
Yes, sir. The reference point is 25 degrees, so enthalpy of or feed will be 0, sir.
How it will be 0? Feed is not at 25, feed is at 300 degrees centigrade.
No, means at 25 degree means you want to calculate
At 25. So
20.
we are saying our reference condition is 25 degrees centigrade, and at this condition we are saying oxygen gas has 0 enthalpy, nitrogen gas has 0 enthalpy, SO2 gas has 0 enthalpy, SO3 gas has 0 enthalpy. Is that what you want to say?
Yes, sir.
Okay. Okay, now go forward.
So we want to calculate the enthalpy of inlet, sir, first.
Okay, enthalpy of stream number 1. Let's give some stream numbers. Let's call this as stream number 1. Let's call this as stream number 2. There are only 2 streams in the problem. Okay. Enthalpy of stream number 1. What does stream number 1 contain? 9 gram moles of SO2, 9 gram moles of oxygen, and 82 gram moles nitrogen. Okay. Now tell me enthalpy of the stream number 1 with respect to this reference.
So 9 into.
Okay. So enthalpy would be 9 into
0 plus integration of 298.15 into
300 degrees centigrade. So that's 573.15.
Yes, sir.
Okay.
So the ABC constant of SO2.
So shall we just say Cp of SO2 into dt?
Yes, sir.
Okay.
Plus 9 into 0 plus 290 same limit, sir, and of O2 plus 82 into same, sir, of 0 plus.
Yeah, correct. I'm just writing so that everybody understands clearly.
Sir, I consider the reaction is taken at 450 degrees Celsius. So
that's okay. That's okay. Atharva, let us go step by step. I have understood your what you are trying to say. So
we finish the enthalpy of inlet, sir, here.
We have finished. So this is what are the units here?
Yes, sir. We want to convert the limit into kilojoules, sir. Integration part.
So this value, if you calculate, Cp is in calories. So this would be in terms of calories, right?
Yes,
we
sir.
have to convert to kilojoules. So this whole thing we will take, multiplied by 4.18 and divide by 1000. So this enthalpy now will be in terms of kilojoules. Okay, now.
So you want to calculate the stream 2 enthalpy.
Enthalpy of stream 2
is equal to 9 minus x.
Same way, 9 minus x, 0 plus 298.15 to 450, meaning 723.15 Cp SO2 dt. Okay.
Yes, sir. Plus 9 minus x by 2.
There is a small mistake you are making, but that's okay. You go ahead. I will explain that later.
Let's say 82 into.
Wait. Cp not SO2. It is Cp of oxygen plus 82 into 0 plus 298.15, 723.15 Cp of nitrogen dt plus.
You want to convert into kilojoule?
Sulfur trioxide किधर गया?
So we have calculated first only, sir.
Sulfur trioxide SO2 calculate किया ना? SO3 किधर calculate किया?
So enthalpy of reaction at 450 degree.
अच्छा ठीक है, enthalpy of stream, but stream 2 has SO3 also, na? I have understood what mistake you are making, Atharva, but I just want you to, whether you are
I didn't get it that what you were saying.
stream 2, we are finding enthalpy of stream 2.
Yes, sir.
Stream 2 has SO2, stream 2 has oxygen, stream 2 has nitrogen, but stream 2 also has SO3 ना, उसका किधर गया, तुम क्या कर रहे हो, उसके लिए क्या कर रहे हो?
So I calculated the reaction at 450, sir, too, so that will be same, na?
Same means what? I have not understood. अच्छा ठीक है, okay ठीक है, you go ahead. Here, so you want 298 to 723 or 573 to 723. This limits of integration, what do you want?
Sir, 290 means we taken 25 degree. Sir.
Okay, 298.1. हाँ ठीक है. Now this whole thing multiplied by 4.18 divided by 1000. Okay, now tell me what?
Plus, sir, enthalpy of reaction at 450 degrees Celsius. Into X, sir.
X moles are reacted. Okay. Okay.
Stream 1 in.
Now. Okay, Atharva, now what?
Enthalpy of stream 1 equal to stream 2. We will get X, sir. Enthalpy of stream 1 equal to enthalpy of stream 2. It is adiabatic process.
Enthalpy of stream 1 is equal to enthalpy of stream 2. And then solve for X.
Yes, sir.
Okay. So what X you get now? So whatever error you had made.
I made a calculate mistake. I will calculate again. I consider temperature in Celsius, sir.
Okay. Okay, maybe that's why your X is 44 and other people are getting 55. Okay. Fine. If you have understood what Atharva says and you want to do it by Atharva's method, that is fine. Let me show you one more method or one more way of talking about it, one more way of thinking about all this problem. Okay, so let us not try to calculate anything at all. Let us try to imagine what is happening in the process in terms of enthalpy versus temperature graph. So this is our 25 degrees centigrade, and 25 degrees centigrade we are saying, yes.
I have a doubt. Sir, in enthalpy of stream number 2, why haven't we take enthalpy of SO3?
Well, I don't know because you can ask Atharva. Atharva, you want to reply? Atharva, you want to reply?
You consider reaction is taking place at 450 degrees. So
Atharva has already considered, because he has considered reaction is occurring at 450 degrees centigrade. Rishikesh, that will not satisfy you.
So if we calculate 300 plus we do heat of reaction of SO3, we'll get same answer, sir.
Correct, Atharva. Rishikesh, have you understood?
Sir, can you please repeat? It was lagging, sir.
What was lagging? You were not able to hear clearly.
Yes,
it doesn't matter. Okay. So Atharva is saying that he has already considered enthalpy of reaction, and reaction is occurring at 450 degrees centigrade. Therefore, he does not need to consider separately. He does not need to consider separately SO2. He does not consider separately SO3 because this enthalpy is automatically there as X moles of SO2 gas plus 0.5 X moles of oxygen gas, giving you SO3 gas. This is automatically there at 450. He has only considered reactants are at 450 degrees centigrade and they get converted to SO3 at 450 degrees centigrade.
Yes, sir, I understood. Thank you.
ठीक है, so it doesn't matter even if you have not understood. It doesn't matter if you are not convinced. Let us think. Let us not do any calculations. Let us not do any methods. Let us not remember any methods. Let us just try to visualize what is happening in the reactor. What is happening in the reactor? The reactor is adiabatic. All those who have understood what Atharva has done, fine, you can continue using that. All those who are not comfortable with what Atharva has done, I will show you some method, I will show you some discussion, I will discuss some things, but I want you not to solve the problem. First, I want you to visualize what is happening in the reactor. If you are able to visualize what is happening in the reactor, solving the problem is a child's play. Any kid in 10th standard or 11th standard can do it. You are way above that. All right. We have assumed that in the reactor, X gram moles have reacted. All right. Now, here is one possible way of visualizing what is happening in the reactor. So imagine that 25 degrees centigrade, we have set enthalpy to be 0. We have set enthalpy to be 0 for, let's say, SO2, oxygen, nitrogen, SO3. All the components that are there. This is one way of doing it. It is not the only way. Okay. There are multiple ways of doing it. I will show you 2-3 ways of doing it. But you pick whatever method you feel comfortable with. I'm just showing you one method which is easy to sort of understand. So we are saying that these are our, at this reference condition of 25 degrees centigrade, enthalpies of SO2, SO3, oxygen, nitrogen, all these have 0 enthalpy, like our potential energy we have defined. Okay. Now, what is happening in the reactor? In the reactor is at 300 degrees centigrade inlet, reactor outlet is at 450 degrees centigrade. So if you think about what is happening in the reactor, this is our reactor. Whatever is happening between these two dotted lines is our reactor. Do you agree with that? So, in this reactor, SO2, oxygen, nitrogen are entering. They are entering at 300 degrees centigrade, and they would have certain enthalpy at 300 degrees centigrade with respect to the enthalpy at 25 degrees centigrade, which is what Atharva has already calculated for us. Enthalpy of stream number 1. This value. Okay. I am assuming all of you can do integration yourselves. So this integral, you can calculate and get the values. Okay. Now, in the reactor, what is there? In this reactor, there is catalyst. Catalyst. All right. Vanadium pentoxide is our catalyst. Okay, let me draw the catalyst. I want you to visualize, not solve the problem. If you are able to visualize, problem will be solved in less than 30 seconds. If you are not able to visualize, problem will take 2 hours and you will go around in circles and nothing will happen. Okay. So suppose these are catalyst particles. SO2 gas is coming in, oxygen gas is coming in, nitrogen gas is coming in. When this gas encounters catalyst, some reaction will happen. Okay, let's say out of this 9 gram moles at the entry, let me draw this little bigger. Let me draw this little bigger so that I can explain properly. This is our reactor. We don't know how many moles are reacting, but incoming moles are 9 moles and 82 moles. Now I'm going to break down this reactor into small differential elements, small pieces. I'm going to break down this reactor into small pieces. Can I do that? Yes, no?
Yes, sir.
Yes, sir.
This is the outlet. So you have all understood what this kind of symbol means, right? It is just a continuation. It's a long continuation, but just to show it in a small way, we are just writing these squiggly lines, if you like. You've done that in your engineering graphics anytime? Yes, no? No, you've not done in engineering graphics?
So we have done, but not something like that.
Okay.
Yes, sir.
You used to show something else? Anyway, doesn't matter. You understand that this is just a depiction. That reactor is continuous. It is long, but I'm just shortening it. All right. Now I'm going to break down this reactor into small pieces. Do you agree? I mean, there's no question of agreeing. Do you permit me to break down the reactor in small pieces?
Yes, sir.
Okay. Now, because the whole reactor is adiabatic, can I also assume that each of these small pieces are also adiabatic?
Yes, sir.
Yes, sir.
Okay. Now, this small piece of reactor, I am going to say this small piece of reactor is differential, meaning this small piece is tending to 0. The length of that small piece is tending to 0. So I'm just saying that in this first small piece, let us say 0.1 gram moles of SO2 react in the small piece, in every small piece. Is that okay? Can I assume that 0.1 gram moles of SO2 react in every small piece? Can I make that statement? And if you don't like this 0.1, you can take it 0.01. If you don't like 0.01, you can take it 0.0001. Okay. Just to illustrate the calculation, I am just taking 0.1. Do you permit me to do that? We have not defined how small that small is. Therefore, it is okay to take 0.1. I mean, is that okay? Can I go ahead? Somebody say something.
Yes, sir. Yes.
Yes, sir.
So I'm going to require people to interact. So please feel free to unmute yourself and talk to me. Okay. So in this first piece, so if I take, let's say, SO2, oxygen, nitrogen, entry 9982, these are all gram moles we are writing. After first piece, what would I be left with? I would have 8.9, I would have 8.95, 82, SO3 0.1. Do you agree with that?
Yes, sir.
Yes, sir.
After second piece, it would be 8.8, 8.9, 82, and 0.2. After third, it would be 8.75. Sorry, not 8.7, 8.7, 8.85, 82.3. After fourth piece, it would be 8.6, 8.8, 82.4, and so on. Do you agree with that? Material balance.
Yes, sir.
Okay. Now, what is the temperature at the entry? What is the temperature at the entry?
300 degrees Celsius.
300. So if I say temperature in terms of degrees centigrade, it would be 300 degrees centigrade. After the first piece, it is an adiabatic piece. Whatever 0.1 gram moles of SO2 that have reacted, how much heat would have been generated? I don't want the value, I just want to how to calculate. Heat generated by way of exothermic reaction, how much would that be?
0.1 into the heat of reaction.
0.1 gram moles of SO2 multiplied by what?
98.2.
98, Hardik, 98 is what?
Heat of reaction.
But this is at 25 degrees centigrade, Hardik.
Okay, sir. Sorry, sir. Yes, sir.
So,
Heat of reaction at 300 degrees Celsius.
correct. Delta H at 300 degrees centigrade for this reaction. Do you agree with this?
Yes, sir.
Oh. So because of this, now the SO2 will get heated up, oxygen will get heated up, nitrogen will get heated up, and SO3 also will get heated up. Do you agree with that? Because it is adiabatic, that whatever this heat is generated, that is not lost to the surroundings. All that has gone in heating up the SO2, oxygen, nitrogen, and SO3. Do you agree with that? So the outlet temperature would be more than 300 degrees centigrade. Let's just say it is 305 degrees centigrade. We don't know the actual value. Actual value will depend on the CP values. But let us just assume that it is 305 degrees centigrade. Why it has gone from 300 to 305? Because this much amount of heat is generated by way of exothermicity of the reaction. Do you agree with that? How much heat is generated? Delta H for the reaction, is minus 98 at 25 degrees centigrade, 98 point something. So the heat that is generated would be minus of delta H at 300 degrees centigrade reaction. I'm just talking heat of reaction, heat that is generated. I'm just saying because it is an exothermic reaction, this minus sign indicates the exothermicity. So the heat that is generated is just the mod of this minus 98. Do you agree with that? So rather than writing mod, can I just say it is minus delta H reaction? Or if you don't like this minus of delta H, can we just simply say is the mod of delta H at 300 degrees centigrade for the reaction? Mod, absolute mod is the value, right? Do you agree with that? Minus sign is just indicating to us that it's an exothermic reaction, heat is generated. Do you agree with that?
Yes, sir.
Yes, no?
Yes, sir.
Yes, sir.
Yes, sir.
And do you also agree that temperature will go up from 300? I'm just saying it is 305, but it could be 304, it could be 301, it could be 300.88, whatever. It will depend on the CP value. Is everybody comfortable with this one small piece of the reactor? If everybody is comfortable with this one small piece of the reactor, then we will go forward to the second piece of the reactor.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
3-4 people are comfortable with the first
Okay, sir.
piece.
Yes, sir.
Yes, sir.
Yes.
Out of 54. Okay, now go to the second piece of the reactor. In the second piece of the reactor, 0.1 moles are reacting. So how much heat is generated by way of the exothermic reaction in the second piece? It would be 0.1 gram moles of SO2 multiplied by heat of reaction at 305 degrees centigrade. Do you agree with that? Because reaction is happening at 305 now. The gases are entering the second piece at 305. Do you agree? Do you disagree?
Yes, sir.
Rishikesh?
Yes, sir.
Sir, could you please repeat the last point?
Yeah. In the second piece, that is this is our first piece. This is our second piece. This is our third piece. This is our fourth piece of the reactor. This is our fifth part of the reactor, sixth piece of the reactor. Right? Now we are considering the second piece. In the second piece, what enters is what is
SO2, O2, N2, SO3 at whatever temperature according to the CP.
305 degrees centigrade. Right?
Yes,
This is what is entering the second piece. What is coming out after the first piece is what is entering into the second piece. So in the second piece, in the second part of the reactor, second piece of the reactor, SO2 is entering, oxygen is entering, SO3 is entering, nitrogen is entering, but they are entering at 305 degrees centigrade. Do you agree with that?
Yes, sir.
So the amount of heat generated in the second piece of the reactor would be the 0.1 gram moles of SO2 that react multiplied by the mod of heat of reaction, but that reaction is now occurring at 305 degrees centigrade because the reactants are at 305, catalyst is at 305, so reaction is happening at 305. Do you agree with that?
Yes, sir.
Yes.
So that much amount of heat that is generated will again heat up the SO2, oxygen, nitrogen, and the gases that will leave the second piece. These are the gases that leave the second piece and enter the third piece. They would be at a temperature higher than 305. Let us say they are at 310 degrees centigrade. Let's just not take 55 degree. Let us just take some random values, 309 degrees centigrade. Do you agree with that?
Yes, sir.
Now we go to the third.
Yes, sir.
Now we go to the third piece of the reactor. In the third piece of the reactor, what enters? 8.8, 8.9, 8.2 and 0.2. They enter at 309. Again 0.1 mole reacts. So the amount of heat generated in now the third piece would be 0.1 gram moles of SO2 multiplied by not 305 now, it will be 309. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Do people agree with that? Nobody agrees, nobody disagrees.
Yes, sir.
Yes, sir.
Agree, sir.
Only 3 people are agreeing. Only 4 people are agreeing.
Yes, sir.
Yes, sir.
Only 4 people are listening. Arya, are you okay?
Yes, sir.
Yes, yes, sir.
Okay. Now let's go to the fourth piece. So after the end of the third piece, let's say temperature becomes 314 degrees centigrade. Right? Or let me just take some random value. Let's say it becomes 317 degrees centigrade. Now in the fourth piece, 8.7 moles are entering, 8.85 moles are entering, 82 moles are entering, 0.3 moles are entering, but they are at 317 degrees centigrade. So heat generated by way of reaction in the fourth piece is 0.1 gram moles of SO2 multiplied by 317. Do you agree with that? And then that will heat up the gas to maybe, let's say, 325 degrees centigrade. Do you agree with that? Anybody agrees? Anybody disagrees?
Agreed, sir.
Hardik, you have raised a hand. If you have a question, just
Sir, by mistake, sir. Sir, by mistake.
Okay, fine. Just otherwise, just unmute yourself and speak up. No need to raise any hands. Just
okay, sir.
Unmute. All right. Let us depict all this. It's difficult to maybe visualize in terms of a table. Let us depict all this on this graph. So our 982 enter. What enters after the first piece? It has been heated up to 305, then 309, then 317, 325, right? It is going like this. Do you agree with that?
Yes, sir.
And here I have all my 9 minus x, 9 minus 0.5x, 82 and x of SO2, O2, N2 and SO3. Do you agree with that? Right. So in this part, I have delta H for the reaction I need to consider at 300 degrees centigrade because 0.1 gram moles are reacting at 300 degrees centigrade. In this part, I need to consider delta H for the reaction at 305 degrees centigrade. In this part, I need to consider delta H for reaction at 309 degrees centigrade. In this, no, what was it? 305, 309, yes. Whatever I had made. This is 309, right? This is next part is 370. In this part, I have to consider delta H at 317 degrees centigrade. Do you agree with that?
Yes, sir.
Yes, sir.
Because enthalpy is a state function, rather than traveling by this black path, rather than traveling by this black path, can I not travel by this red path? Or can I not travel by this red path? Well, let's take another color. Otherwise, all confusion will happen. Why not travel by this blue path? In the red path, what is happening is that reactants are heated to 450 degrees centigrade and reaction happens at 450 degrees centigrade. In this blue path, the reaction is happening at 300 degrees centigrade and all the products are, product means all the gases are getting heated to 450 degrees centigrade. Right? Think about this. Let's have a break of 5 minutes. Let's have a break of 5 minutes. What we have done, we are only trying to visualize. We are not solving the problem. We are assuming that we have broken the reactor into different pieces. First piece, second piece, third piece, fourth piece, fifth piece, sixth piece, 25th piece, 578th piece, right? And every piece, the reaction is happening at different temperature: 300, 305, 309, 317, 325, 338, 341, 345, 357, 398. Every piece, the temperature is different, the composition is different. Instead of that, instead of this black path, going from reactant to product slowly, can we go from reactants to products by this blue path and heat up all the products from 300 to 450, or go by the red path, heat up all the reactants from 300 to 450 and do the reaction at 450. Let's have a break of 5 minutes. Let's understand what we have been talking about. Let's try to visualize. If we are able to visualize, the problem will get over in 30 seconds. Guaranteed. Break of 5 minutes for you to think, not for any other activity. Don't do WhatsApp and this and that in that 5 minutes. Think about what we have talked about for the last 30-40 minutes. 5 minutes, we will meet again. Okay, any question in the couple of minutes? I'm going to have break for another 2 minutes, but another 1 minute maybe, but any question in the meantime?
Sir,
Yes.
sir, I had done the problem by this method only.
Okay. Doesn't matter. If you have got the answer, doesn't matter. It's good.
Yes.
If you have got the answer, that's good. We are discussing so that this is the first problem that we are doing for enthalpy with reaction. So therefore, we are discussing in a lot more detail so that everybody's doubts will be cleared or everybody will have a method to work by. Okay, shall we start?
Yes, sir.
Yeah. So if we are traveling by this blue path, you might want to draw this in your notebooks also. If you are traveling by this blue path, what enthalpy balance we are going to write? We are going to write balance of enthalpy over the control volume, which is our reactor. This is our control volume. This is our reactor. This is our control volume. So blue path means we are doing reaction at 300 degrees centigrade. So the balance of enthalpy that we would be writing, reference, let me write 25 degrees centigrade, SO2, oxygen, N2, SO3 have zero enthalpy. So enthalpy over this control volume reactor with the blue path. So this is enthalpy of stream 1 at 300 degrees centigrade with respect to reference plus heat generated by a reaction due to X gram moles of SO2 reacting at 300 degrees centigrade must be equal to enthalpy going out, which is nothing but stream 2 at 450 degrees centigrade with respect to the reference. Just like we are writing enthalpies, because we are writing enthalpy coming in, enthalpy going out, because we want it to be just like material balance. How we write for material balance? That 9 moles have come in, X moles have reacted. So what goes out is 9 minus X. X moles of SO3 have generated. What comes in, SO3 moles that come in is 0. X moles of SO3 have been generated. So what goes out is 0 plus x. Just like we have been writing for materials. Just like we have been writing for moles in plus moles generated minus moles reacted is equal to moles going out. For SO2 it is 9, nothing generated, x reacted, so outgoing is 9 minus x. For SO3 it is 9, sorry, SO3 it is 0 plus x generated, nothing reacted, so outgoing must be x. For oxygen, moles in 9, generated nothing, reacted 0.5x, so outgoing must be 9 minus 0.5x. Nitrogen, 82 entering, nothing generated, nothing reacted, therefore 82 must be going out. Therefore, to be writing in the same way, we are writing enthalpies also in the same way. We are writing the enthalpy balance also in the same way. Material and energy balance. That's the name of the course. Right? So now all I have to do is find enthalpy of stream 1 with respect to reference of 0 at 25 degrees centigrade. What does stream 1 contain? What does stream 1 contain? Enthalpy of stream 1 with respect to reference, it is 298 plus 300, so 573.15, 9 moles of SO2, Cp of SO2 plus 9 moles of oxygen, Cp of oxygen plus 82 moles of nitrogen, Cp of nitrogen into dt. This is in terms of calories. What is enthalpy of generated or heat generated by way of reaction at 300 degrees centigrade? It is x gram moles of SO2 multiplied by the heat of reaction at 300 degrees centigrade. This is in terms of kilojoules per gram mole, so this will be in terms of kilojoules mod, if you like, because that negative sign is there. Negative sign is only indicating this word, the word generated is indicated by that negative sign. So if I'm talking about generation, I don't need the negative sign here. Do you agree with that? If I multiply by 4.18 divided by 1000, this would be in terms of kilojoules now. So this plus this must be equal to enthalpy of stream 2 with respect to reference. This would be integral from 298.15 to 450, so that is 723.15, 9 minus x multiplied by Cp of SO2 plus 9 minus 0.5x Cp of oxygen plus 82 Cp of nitrogen plus x Cp of SO3 dt. Solve for x. This plus this must be equal to this. Solve for x. Is that okay? Let's just take one or two more problems so that we are all comfortable doing all these calculations. Right? Any doubt so far? So I would recommend that we take the blue path. Atharva took the red path, but that's okay. Atharva, you have corrected your answer now. Are you getting 44 or 55?
So I have to calculate, sir.
Ajay,
It is
okay.
first calculation.
Okay, any doubt? Let's take a couple of more problems so that we are all comfortable with doing all these calculations. Any doubt? Any question? Anybody awake? Nobody is awake.
Yes, sir.
You are
Yes, sir.
Any doubt? Any questions?
No doubt.
No doubt, sir. No doubt.
Okay. Let's take one more problem, just in a very similar problem, only different gas and different things. But I will just give you some simple situations so that we avoid this lengthy integration. This integration takes time, and then there are more chances of making mistakes in all this. Obviously, this also will have to convert to 4.18 and divide by 1000, so that this also is in kilojoules. Okay. All right. Let me give you a simplified problem so that we don't do all these integrations. The chance of going wrong are less, just so that our concepts are clear. So imagine our reactor again. Similar problem, just a different set of reactions. But I will make the CP values simpler. Okay, so we have, let's say, oxygen, nitrogen, and ethylene. So ethylene oxide reactor. Do you remember the ethylene oxide reactions? Ethylene plus half oxygen giving you ethylene oxide. Do you remember? Yes, no? Nobody
Yes,
remember?
sir.
Yes, sir.
But the side reaction also happens that ethylene burns to give you carbon dioxide and water. Do you remember that? Yes, no?
Yes, sir.
So for the first reaction, let us say delta H0F. I'll just straight away give you delta H of reaction. Rather than giving you heats of formation, I will just give you heats of reaction, and that too in all these forms. Water in the gas state. Normally that heat of reaction we talked about would be in the water in the liquid state, but I can always add the enthalpy of vaporization of liquid water to gas water. Then I will get delta H0 for the second reaction for getting H2O in the gas state, because these reactions are at high temperature. So everything is in the gas phase. So I'm making your life simple. This is minus 25. Again, just to give you different set of units, just so that you are comfortable with converting units, it is kilocalories per gram mole of ethylene that reacts. This is minus 315 kilocalories per gram mole of ethylene that burns, combustion. So this is our desired reaction. This is our undesired reaction. Because our desired ethylene oxide is our desired product. Carbon dioxide is not our desired product. All right. So let's say how much? Let's say 10% conversion. And 80% 85% selectivity to our desired product. Okay, recall what conversion means, recall what selectivity means. Go back and revise your notes if you want. You can go back. Okay, let's say I have 100 gram moles of the feed coming in. So 8 gram moles. Oh, sorry. 25 gram moles of ethylene coming. (25 gram moles of ethylene come in), 8 gram moles of oxygen come in, and balance 67 gram moles of nitrogen come in. What goes out? Unreacted ethylene, ethylene oxide that is formed, unreacted oxygen, nitrogen inert does not take part in the reaction, carbon dioxide generated by the side reaction, water generated by the side reaction. Again, you can do the material balance first. Write the gram moles of all of these going out. Let's say this gas comes in at 150 degrees centigrade. Now, I want you to calculate the outlet temperature. Very similar to the first problem. There I had to calculate the conversion. I was given the outlet temperature. Now I am giving you the conversion. I want you to calculate the outlet temperature. So this is one part of the question, or maybe this is question 1 if you like. This is our reactor. Let's assume that it is adiabatic. Very similar to the SO2, SO3 problem. Okay. I'm just going to make your life simple. I'm going to say Cp of all gases is like 7/2 R. So if you want to take, you can take it as 7 calories per gram mole Kelvin. So I have made your life simple. Rather than giving you A, B, C values and integration that we had done for this problem, I'm just making your life simple. I'm saying Cp of all gases is 7/2 R, like an ideal gas, and this is constant, independent of temperature. Have I not done you a favor? Have I not done you a favor?
Yes, sir.
Question 2. Question 2. Same reactor, same reaction, everything same. Same gas comes in, oxygen, ethylene, nitrogen, 8, 25, 67. That's what the value was. Yeah, I just wrote the ethylene first. Yeah, so just so that everybody doesn't get confused. Ethylene, oxygen, 25, 8, 67. Again, same 10% conversion, 85% selectivity to desired reaction. So what goes out will be ethylene, ethylene oxide, oxygen, nitrogen, carbon dioxide, water. Same, everything is the same. Incoming temperature is the same, 150 degrees centigrade. Right? Everything is the same. Everything is the same. Except now we are saying it is an isothermal reactor operating at 150 degrees centigrade. So this product that goes out must also be at 150 degrees centigrade. Now, these reactions are exothermic or endothermic? Say loud.
Exothermic.
Exothermic. Right? So if I have to maintain isothermal conditions, I will require to remove heat from the reactor. Yes or no?
Yes, sir.
Right? So that heat I remove by having a jacket outside the reactor. In this jacket, I will supply saturated water at 130 degrees centigrade. Means it will be at a higher pressure. Steam table. This water will pick up the heat from the reactor so that the heat that is generated by way of reaction is removed by that water. This water is at a lower temperature than this. So heat would be transferred from the reactor to the jacket, where this liquid water at high temperature will pick up the heat, and this will get converted. What will happen to this liquid water that is saturated at high temperature and pressure? What do you think will happen if it picks up heat?
Its temperature will increase.
Temperature will increase.
Sir, it will boil.
I will get saturated steam at 130 degrees centigrade and the corresponding higher pressure. I want to convert liquid water into steam. That requires heat. I remove that heat from the reactor and use the heat to convert liquid water into steam at high pressure. Look at the steam tables video. Why do you think I want to get saturated steam at high temperature rather than allowing this temperature to go up from 130 to 140, 150? Why do you think that? Why do you think I am more interested in generating steam rather than heating liquid water?
Sir, if we allow it to heat, like increase the temperature, then it will go from 130 to 140 to 150. It will approach 150, and the rate of heat transfer will reduce.
Okay, but why do you think I'm interested in making it saturated steam at higher?
Sir, latent heat is more than CP.
Correct. Latent heat is more, and what else?
Then we will require less steam, less saturated water.
No.
So the cost will decrease.
No. No. Now do you see? Now do you see why I'm interested in steam rather than hot water?
Yes, so we can use it again.
Yes, so this steam which is at high temperature, now this is valuable because this can be used as a heating medium somewhere else in the plant. Don't you agree? Rather than taking hot water, that hot water would again get cooled very quickly because Cp is very small. And then if I have to maintain difference of 20 degrees, that hot water is of no use to me. Whereas steam is more useful to me because I can convert it back into liquid water at 130 degrees centigrade. I will get the whole latent heat and I can maintain the 20 degrees centigrade driving force. Do you agree? Yes, no?
Yes, sir.
So saturated steam at high temperature is a very valuable asset for us. We can use it as a heating medium somewhere else in the plant. Whereas liquid water, it becomes so much more complicated to transfer. I will have to transfer so much kgs of liquid water. Whereas if I have to transfer steam, it is a small quantity because latent heat it has picked up. Latent heat is much more, 500 plus kilocalories per kg. Jairaj, you have raised your hand, or it is by mistake?
Sir, it was by mistake. Sorry, sir.
No issue at all. If you have any doubt, please unmute and ask immediately. Don't bother about raising hand. I will not be able to see. Do you agree with that? So now for the second question, I want you to calculate kgs of steam generated per kg of ethylene oxide produced. Will you be able to calculate?
Yes, sir, we'll try.
So for this particular reactor, what control volume we are going to take? This is going to be our control volume. Let's give some stream numbers. Let's call this a stream number 1. Let's call this a stream number 2. Let's call this a stream number 3. Let's call this a stream number 4. What enthalpy balance we can write now for the control volume? Enthalpy coming in plus heat generated by way of the reactions. Two reactions are happening. Desired reaction as well as undesired reaction. Heat generated by way of reactions, desired and undesired, must be equal to enthalpy going out. Enthalpy coming in is because of stream 1 and stream 3. Enthalpy going out is because of stream 2 and stream 4. Find out enthalpies of stream 3 and stream 4. Use the steam table. Alright, so solve these two problems. First one is very similar to the SO2 SO3 problem. Second one slightly different. Okay, solve. If you have doubt, just unmute yourself and ask. I am here only. I am listening. If you have doubt, just ask. I am here. I am listening.
So,
Yes, yes.
so for the previous question, sir, I approached the question in such a way that we were given the formations for SO2 and SO3 at 25 degrees Celsius.
Hmm. Yeah.
So I calculated the formations at 300 degrees Celsius for SO2,
So how did you
N2 and
calculate
O2.
formation? Now, how did you calculate formation at 300 degrees centigrade? Where did you get Cp of sulfur from?
Okay, sir. Oh, that's the mistake I made. I was confused regarding that.
So what you are doing? So Sarthak, 1 second. Let me just write it here. See, this reaction is there, na? Sulfur in the solid state plus oxygen in the gas state, giving you SO2 in the gas state. This is our reaction delta H0. This is nothing but heat of formation. This value I gave you, right?
Okay, sir.
Suppose you want to find S plus O2 giving you SO2 gas. If you want to find this at 300 degrees centigrade, what will you do? So this delta H at 300 degrees, sorry, not delta H0, this delta H at 300 degrees centigrade would be equal to delta H0 at 25 degrees centigrade plus integral from 25 to 98 to 573.15.15 Cp of products minus Cp of reactants into dt, isn't it? What is the Cp of products? That means we will need Cp of SO2 minus Cp of oxygen, it is, and Cp of sulfur dt. Do you agree with that, Sarthak?
Yes, sir. Got my mistake, sir. I did not consider the CP for the sulfur.
Correct. Now that's why we are taking our reference at 25, so that these unknown things can be avoided.
So if in the case we we know the CP of sulfur,
then you can find this way. Then absolutely okay.
So if then we could find the delta H for SO2, similarly for O2 and N2.
Correct. Then I can take reference as 300.
And then we could proceed for the sum.
Correct. Correct. Then you can say enthalpy of incoming stream is 0.
Okay, sir.
Right? That's okay. But I mean these weird things, why should we consider? See, the bigger problem, I mean, these are simple compounds, therefore the heats of formation are known, right? But suppose I give you some compound, let's say here, right? This is phthalic anhydride, right? If I give you this, now I may not know the heat of formation of this compound at 25 degrees centigrade. So delta H0F may not be known. But if this reaction is there, let's say orthoxylene, oxygen giving you phthalic anhydride, plus water, this reaction I can measure delta H0 for the reaction. 0 means at 25 degrees centigrade. This can be measured in the lab. So heat of formations may not be known always, and therefore then we will not know all these CPs of all the reactants. But I can measure the heat of reaction. That's why I have given you this next problem. Here I am not giving you heats of formation. I may not know the heat of formation of ethylene oxide. Right? That's why I'm straight away giving you heat of reaction. That's why we are doing this problem, although it is very similar. because this heat of reaction at 25 degrees centigrade can be measured experimentally. For heat of formation, that compound may not form at 25 degrees centigrade. So there is no way I can take carbon and oxygen and hydrogen, put them in a reactor at 25 degrees centigrade and make ethylene oxide. So I cannot measure heats of formation because reactions may not happen at 25 degrees centigrade. But heat of reaction can be measured at 25 degrees centigrade.
Okay. Thank you, sir.
Yeah.
Sir, can you scroll to the previous problem?
Oh, 1 second. Okay now?
Yes, sir. Yes, sir.
Sir, first answer is coming 396 degrees Celsius.
Your voice is breaking.
Sir,
390,
first answer is coming 396 degrees Celsius.
396. Okay.
Sir, I got 398.
Okay, 396, 398. Do the second problem now. So 396, 398, I'm saying they are same. Any other answer?
Sir, could you scroll down to the question 2?
Yeah. Question 1, any answer, Rujita?
Yeah, so 398.
Ah. Any other answer for question 1? 3 people have got the answer. 396, 398. Yes, they're all same. 397, let's say.
Sir, 386.
380?
386.
Okay, 386. Any other answer to question 1? If you've done question 1, question 2 should take about 5 seconds.
Sir, second one is coming 3.5. Sir, am I audible? Sir, am I audible?
Yeah, Praveen.
Sir, the second one is coming 3.5.
3.5.
5.
So you see how steam can be produced when there are exothermic reactions happening in the plant. .5 kgs of steam. It's a lot of steam. So if you're making, let's say, 100,000 tons per year, you will get 350,000 tons per year of steam. Ethylene oxide is a huge commodity chemical. It is used in, anybody knows where ethylene oxide is used?
Polymers.
Which polymer? Which polymer? Which polymer?
So it is used as a preservative also.
Is there a preservative of for what? What
Preservative
preservative?
of
Which
food items.
Preserving what?
Some food items.
Would you like to eat a food item which has been preserved by ethylene oxide? I doubt.
Sir, pesticide.
You people are guessing, or you people are?
No, sir, Google, I guess.
Google. Google can't tell you anything.
So, starting material for other products.
Like what?
So, like for other alcohol.
Sir, it can be used to make ethylene glycol.
Yeah, of course, ethylene glycol. We have seen ethylene glycol is used in making polyester. So, to make alcohol, which alcohol you want to make from ethylene oxide? Ethylene oxide, if you hydrolyze, you will get ethylene glycol. If you hydrogenate, you will get ethyl alcohol. People make ethylene oxide from ethyl alcohol. Ethylene oxide is more valuable than ethanol, ethyl alcohol.
The other long chain alcohol,
Like what? You are almost there.
propanol.
Ethylene oxide, how will you get propanol from ethylene oxide?
So Grignard reagent.
Ore power, Grignard reagent. Which Grignard? Methyl magnesium bromide.
Yes, sir. Methyl magnesium bromide.
Ore baap re. How do you make this? This seems a very nice reaction in your 12th
So
standard.
in the laboratory, yes, but
Correct.
not on industrial. Not on industrial scale.
In the laboratory and in the class textbooks, this Grignard reaction seems like a very nice reaction. And it's like magic. It works like magic. Isn't it? Don't even think about making Grignard reagents. They're so difficult to make. You need anhydrous conditions. Only then you will get Grignard reagents. Making anhydrous conditions is next to impossible or very, very, very difficult. So all the chemistry that you have seen with respect to Grignard, most of the people can easily afford to forget. All that 12th standard Grignard chemistry is not at all useful for 99.99% of the products. 12th standard chemistry is outdated, it is irrelevant, it is uneconomical and infeasible. The sooner you forget, the better it is. That's why we have 2 organic chemistry courses. Ethylene oxide is used to make ethoxylates. They are reacted with a long chain amine or a long chain alcohol, and then you get ethylene oxides gets added to this. Multiple ethylene oxides get added here. Or they get added here. And these are ethoxylates, these are all surfactants, non-anionic or anionic surfactants. And these surfactants are used in all possible places, right from toothpastes to drilling oil wells, crude oil wells. You people should read labels of all the products that you use at home. Toothpaste, cream, shampoo, all the kind of products that you use at home. Just read the labels, what it contains. And then you will see so many surfactants are used in all these formulations. Alright, so would you be able to solve? Would you be able to solve these 2 problems? We can stop for the day.
Yes.
Yes, sir.
Yes, sir.
Okay. So we'll stop for the day, do this as homework. These 2 problems as homework. I will share some more problems from the past papers in a problem sheet. That is one. And second, I will share 1 or 2 more problems on the recorded video lectures. Okay. So do all of those. Okay, shall we stop for the day?
Okay, sir.
Stop recording. If any of you are coming to ICT tomorrow or Monday, you are most welcome to drop by my office.